Namaskar. I'm Harpreet Kaur and I welcome you all to a live and interactive session. Yes, a session which you'll be watching on many of the platforms. This is a very special webinar series presented by Department of Education, Science and Mathematics, NCERT, New Delhi. Well, the series title is Listening to Learn, yani Sune or Seekhe. Today we are in the 97th edition of our webinar series and the topic that we have taken up today is amazing. This is origin of Mars and we will be telling you all the details in a while. Of course, we have two eminent personalities in our studio which will be conducting a very fruitful conversation related to the topic today. Now, as you all know that under this initiative of webinar series Listening to Learn, we have presented many sessions in the previous months or year or so. If you want to watch our previous sessions, if you want to know what all treasure is there, you can definitely log on to the link ncert.nic.in/webinar_series.php. And we all want you to share your feedback regarding this session with us. So you can always write an email to us and the email ID is dth.class12@cert.nic.in. And today, who is there with us? Let me introduce all of you to the man behind this entire initiative, the man who started this and the man who is responsible for bringing such great minds to our studio. Let's welcome Dr. Gagan Gupta from Department of Education in Science and Mathematics, NCERT, New Delhi. Sir, namaskar and very warm welcome.
नमस्कार हरप्रीत जी। दोस्तों, आज दिल्ली का मौसम बहुत अच्छा है, थोड़ी थोड़ी धूप खिली है, बहुत सुहाना मौसम है और आज मेरे साथ चेन्नई से मेरे साथी डॉक्टर वी रविंद्रन जुड़े हुए हैं, जिनके बारे में मैं आपको थोड़ी देर में थोड़ी ज़्यादा विस्तार से बताऊंगा। आज का जो हमारा टॉपिक है वो बहुत यूनिक टॉपिक है, प्योर साइंस से जुड़ा हुआ टॉपिक है। आज हम अपने 97th एडिशन में साइंस के गूढ़ विषयों पर, गूढ़ उत्पत्तियों पर वापस लौट रहे हैं। साथियों, आपको याद होगा कि अगस्त 2021 से हमने इस सीरीज़ को शुरू किया। हमने हेल्थ से जुड़े हुए विषयों को लिया, हमने विज्ञान के विभिन्न आयामों से जुड़े हुए विषयों पर बात की, मेडिकल क्षेत्र के विषयों पर बात की, हमने आपको दिल की सैर कराई, फेफड़ों की सैर कराई, विभिन्न अंग किस तरह से कार्य करते हैं उसकी बात कराई, हमने इन विट्रो फर्टिलिटी पर बात की, हमने बैटरीज पर बात की, हमने न्यूक्लियर पावर पर बात की, इंडिया स्पेस प्रोग्राम पर बात की, आर्टिफिशियल इंटेलिजेंस पर बात की। इस तरह से जुड़े हुए बहुत सारे विषयों पर हमने बात की। ये सारे प्रोग्राम आप, जैसा मेरे साथी हरप्रीत ने बताया, आप हमारे ncert.nic.in के इवेंट सेक्शन में जाकर आप सारे प्रोग्रामों को देख सकते हैं। आज इसी क्रम में आज 97th एडिशन है, 97वां हमारा संस्करण है। आज मेरे साथ डॉक्टर वी रविंद्रन जुड़े हुए हैं मद्रास से, जो कि द्रव्यमान की उत्पत्ति कैसे हुई, द्रव्यमान की सोच किस तरह से आई, मैटर किस तरह से बना, किस तरह से पृथ्वी से में मास की या मास की अवधारणा को जन्म मिला, हाउ वी गॉट द होल आइडिया ऑफ मास इनटू एग्जिस्टेंस। दिस इज अ वेरी इंपॉर्टेंट टॉपिक एंड दिस इज रिलेटेड विद द मॉडर्न रिसर्च, modern scientific research. My friend Dr. V. Ravindran is ready to take this complex situation to the school children. He is going to speak in very simple terms, very understandable terms to a layman. So before I give it to Dr. V. Ravindran, let me introduce you my friend Dr. V. Ravindran, who is currently the professor and director of the Institute of Mathematical Sciences, Chennai, which is a Department of Atomic Energy Unit at Chennai. Ravindran got his doctoral degree from the IMSC, that is the Institute of Mathematical Sciences as well. Dr. Ravindran has been the postdoctoral fellow at the Tata Institute of Fundamental Research, Mumbai, Physical Research Laboratory, Ahmedabad, and the Deutsches Elektron Synchrotron DESI, Juthen, Germany. Professor Ravindran is also an adjunct professor at the Indian Institute of Science Education and Research, Mohali, which is called ISER Mohali. Prior to joining Institute of Mathematical Sciences in 2012, Professor Ravindran was a faculty member at the famous Harish Chandra Research Institute, Prayagraj, during 1999 to 2012. This institute is popularly known as HRI Allahabad. Dr. Ravindran is a fellow of the Indian Academy of Sciences, Bengaluru, the National Academy of Sciences, Prayagraj, and the Academy of Sciences, Chennai. A decorated scientist, Professor Ravindran is with us today, who has been the visiting scientist at the Japan Society of Promotion of Sciences in 2005, FOM visiting Professor Lawrence Institute, the Netherlands, during 2005 to 2007, visiting scientist, Theory Group, DESI, that is Deutsche Elektronsynchrotron DESI, Germany. He has also been the visiting scientist of the Theory Group at the European Organization for the Nuclear Research, popularly known as CERN, Geneva, and visiting professor at the Pauli Center for Theoretical Studies, Zurich, Switzerland, during 2017. My friend Dr. Ravindran is a theoretical high energy physicist, and his area of research is precision physics relevant for physics studies at high energy colliders such as Large Electron Positron Collider, is called LEP, Tevatron, Large Hadron Collider, Electron Ion Collider EIC, etc. For the Large Hadron Collider, Ravindran has been involved in predicting inclusive rates for the production of Higgs bosons, alternatively the God particle, or a pair of leptons in Drell-Yan process. For results have played an important role both in discovery of the Higgs boson at the Large Hadron Collider at CERN. We thank Dr. Ravindran and the Institute of Mathematical Sciences and the Homi Bhabha National Institute for collaborating with the National Council of Educational Research and Training. We believe that we will continue this kind of collaboration in the days to come ahead. Welcome Dr. Ravindran, and it's all yours now. Thank you.
Namaskar. Let me first thank Dr. Gagan Gupta for his wonderful initiative of bringing science to the mass. That's an important thing that I think our country needs now, and I think he has been doing wonderfully, and I congratulate him, and also want to thank him actually for giving me this opportunity to be part of this this event that has been going on for a while actually. So thank you Dr. Gagan Gupta for inviting me to this very nice program, and I'm happy to be part of it actually. Today I want to actually sort of share some of the ideas that been developed over the years actually, not just last decade or last century. It is several centuries actually that evolved and provided understanding of the science we know today and the technology that we are all familiar with. Okay, that's the origin of mass. This is a question that is not new to the current age. It's a question that people asked very long ago. Like people, the famous philosophers like Plato asked this question: what is everything made up of? What are the fundamental building blocks? And of course, those were the times that there were no things like electricity, there's no trains, there's no aeroplanes and things like that. So questions were actually very fundamental questions. Now we have better understanding, and of course those questions are very important for development of science, our understanding of nature. Okay, so this question that what makes our entire universe, entire thing that we see around us actually, the simple answers that they found was actually, now it would look very simple, okay, but it is okay that those were the answers. That you have to worry about more about questions than answers. So the simple answers were air, fire, water. Okay, and now the question can be sort of generalized more, okay, because we can see around, we can see up, and see the sky, this vast sky that we see every day night. We can ask the question, and the vast sky, what we see is actually these blinking stars, okay, and those blinking stars, bring in not only joy, also several questions. What are those questions? We can ask the question, actually the stars that we see, that's why called visible matter, okay, what are these stars, what brings us actually, how they shine, and you can also ask questions like, one question that I wanted to ask actually, what makes them, the stars that we see, what is its composition, okay. These are questions that I can ask in mathematics, in scientific terms. You can ask what is the mass of the visible matter around us. Visible, I say, because that's something that we can see, okay, through, like electromagnetic waves. The visible light is, part of the electromagnetic spectrum that we have. Radio waves, X-rays are all examples of part of electromagnetic waves. So this question people asked, before answering this question about what we see around us, on the sky, let's ask a even simpler question actually, before we go and do this, find the answer. The simpler question would be to concentrate on our planetary system, okay. We all know that we revolve around sun, okay. Sun, we think it's almost like a stationary object with respect to us, and we revolve around them actually. Now there are planets that revolve around them. So physicists have found a way to actually find out, whether the sun exists. Of course sun exists because we can see the sun, very bright sun we can see in front of us every day, morning to evening, okay. Now you can ask the question, suppose I close my eyes and ask the question whether I can find out the sun exists, okay. There is a way to do in science, okay, in physics, thanks to Newton, okay. We know that velocity, radial velocity of every planet that we see, okay, even if you do not see the sun, okay, will be related to their radius through the square root of 1 by r actually. So if you know the distance, okay, of the star, we can tell you what is the orbital velocity, or if you know the orbital velocity of the planet, we can actually tell how far the planet is actually. So there is a nice relation between velocity, orbital velocity of the planet, which is revolving around some massive object, and the distance of that object from the center of that this massive object, which is sun, okay. Now you can plot the orbital velocity of every planet that we can actually see against the distance, okay. These two quantities are measurable because we have many equipments that can actually measure this orbital velocity as well as the distance, and the curve looks something like this actually. So now you can actually very nicely tell where what is the velocity, orbital velocity of a planet, and what how far it is actually. And this also tells you something very interesting. This relation between this velocity, orbital velocity, and the radius is related by two constants. One is this Newton's constant g, and another constant m. So this, what is this m? This m is nothing but the mass of the the massive object that makes all these planets to revolve around it, okay. That is the mass of the sun. Even if you do not know this, the existence of sun, by this, using this plot, you can actually tell there exists a massive object at the center of this revolving planets, okay. And we can also tell what is the mass of the planet by looking at this curve, because if you know r and v and the gravitational constant, you can uniquely define m, okay. For different planets, you can find out what is this m, and one finds that planets and the radius and velocities, you can determine m. So even if you do not see sun, for example, sun is dark, let us say, and you do not see them, just from this plot, the motion of the planets, you can actually predict what is the object that is sitting and that is responsible for making all the planets to revolve around it actually. And it was found using this plot that mass of the sun is about 10 power 30 kilograms, really huge. Okay, that's something that you can get from science. Okay, so mass of the sun you can find out just by looking at the motion of the planets. That is the message.
All right. Well, what
That
sir
I
is
want to give.
yeah.
So if I know the motion of the planets is, so the biggest system now is actually what we see in the sky, that is our visible universe. Now you can ask the same question, can I find out what is the mass, or some object that is responsible for the motion of all these stars actually. Can you find out is the mass of the the universe that we see by looking at the motion of all the stars, galaxies, okay, etc., etc. So this is just the same question that I asked for the planetary system. Now I am asking the same question for a case of visible universe that we see around us actually, and the answer is actually very shocking, because if you look at the motion of all these galaxies using our telescopes or satellites, what we find is very different from what we found in the case of the planetary system. What we saw in the planetary system was a curve like this, which was going down. Now you see a curve which is going up actually. Okay, I should also mention the name for this plot is called rotation curve. Okay, for rotation curve for the planets I showed in the previous slide, and this is a rotation curve for the galaxies or the universe that we see. And this clearly tells you that there is something not clear to us actually from this plot. What it tells you is that the mass, the visible mass that we see in our universe through our naked eye actually is not actually explaining the curve. Okay, which means there exists huge amount of mass in the universe that we cannot see. Okay, you cannot see them through electromagnetic radiations like X-rays, radio waves, or even visible light that we see every day. Night we see stars. Okay, even that we don't see. Okay, that means there exists a large amount of mass in our universe that our telescopes or our naked eye or our satellites cannot see. That is what this plot tells you actually. So rotational curve plot tells you that there exists large amount of matter that we cannot see. Okay, what we see is only the 5% of the mass that universe possesses. Okay, so today's understanding of our universe is actually we can see only 5% of our universe which is visible. Okay, and the remaining part of the universe is what is called dark because they cannot be detected by any of the equipment that we have at the moment, and they are not visible to our any sophisticated equipments actually. So what we see, understand today in our science domain is only the 5% of the universe. The remaining remaining 73 or whatever 95% of our universe is actually called dark part of our universe, and it is also classified as dark matter and dark energy. Out of which 23% is dark matter and 73% is dark energy, and this is a puzzle that scientists would like to resolve. Okay, so now let's having sort of asked that question and then have real puzzle, I think let's go back and look at what we have understood about this 5% of the universe. So the remaining talk of mine is going to concentrate more on the 5% of the universe that we live in. Okay, what is that actually? So the question that Plato asked centuries back, we have complete answer to it actually. This is the kind of picture that we have, that any matter that we see around us is made up of molecules, molecules are made up of atoms, atoms are made up of nucleus and electrons, and then each nucleus is made up of protons and neutrons, and then each proton and each neutron is made up of what are called quarks, and then the quarks interact among themselves through some particles called vector bosons. So this is the kind of understanding that we have, and this understanding is in some sense is sort of put in a kind of a model called standard model of elementary particles. So the building blocks of the nature that we see, which is the 5% of the universe, is made up of particles like quarks, which is in pink color in this slide, and then the leptons, which are given in the green color in the slide, and the mediators. The particle, the interactions are mediated by certain particles, and those are given in the vertical, this red and yellow color, actually this light yellow and red color boxes actually. Okay, so they are made up of quarks and leptons, and then what they call gauge particle, interacting particle. That is our understanding. Now I will go back to the same question again. How you can actually measure the mass of this 5% of the universe actually, for that matter anything that we see around actually. So how do you measure mass? So simplest way is actually, suppose you give me a matter, I will just count the number of molecules, and if I know the mass of the molecule, I just add them. That is one simplest way of doing actually. Okay. Now how will I find the mass of the molecule actually? Mass of the molecules will be sum of masses of the atoms that constitute them, and then I can actually go on doing the same exercise for atoms. It will be nucleus and electrons, and then if I ask the question, what about the nucleus or nucleons? The nucleons again are made up of quarks and antiquarks and things like that. Now you can add all the masses of quarks, and then you get the mass of the nucleon. Okay. Now what are the masses of the quarks? The quarks which are the building blocks of our nature, okay, they come in different varieties. Okay. They are called up type quark, down type quark, charm, strange, and so on and so forth, and they come with different masses actually. And in terms of these units, GeV, which is about 10 power minus 27 kilogram, so tiny masses. Okay, all these particles share that kind of a mass actually. Okay, so now we can go back to this question that where does this matter get mass from? So if we want to actually really crack this problem, the only simplest solution is actually just count the number of protons and neutrons in our universe. Okay, if you can't count them, and then if you know the masses of the protons and neutrons, you just add all of them, you will get the mass of the universe. Okay, that is the simplest way. Now I want to ask you the following question actually. How tiny this mass is actually? Mass of the proton is extremely tiny. As you can see, it is about 1.67 times into 10 power minus 27 kilogram. Such a tiny object. And similarly for the mass of the neutron, if you think these are first entry in the building block picture, is about 1.67 into 10 power minus 27 kilogram. Such a tiny object. So if I want to calculate mass of the 5% of our universe, is just adding all the protons and neutrons that we see, which are really tiny, add them all and you get the mass actually. Now I want to ask this, I want to probe this. See, I am asking these questions because questions are important actually, and that the curiosity to ask this such questions lead to enormous amount of discoveries, inventions that change the way we live actually. I will give you one simple example later what the weird thinking of Einstein led to a revolution in science actually. I will come back to this. Before that, I keep asking questions simply because it is very important to unravel the nature. Okay, and the question that I am asking now is more difficult than the question that I asked earlier, that is how molecules are actually sharing the mass of various protons and neutrons. Now I will ask the more difficult question. The question is actually, where do protons and neutrons get mass from actually? Okay, I know I can measure protons and neutron masses. Okay, they are very tiny, and but they if I know them, then I can find out the mass of the entire universe actually. Just add all the neutrons and protons. Now I can ask this question, that where do these objects get mass from actually? Okay, they are so tiny. Okay, and we have a picture that proton is not a point-like particle. It's actually a composite. It has a certain structure. Okay, that structure tells you that it is not a point-like. It is made up of certain another elementary point-like objects. Okay, you can break the proton and see it is made up of certain particles called quarks. Okay, for example, if you break a proton or a neutron, you will see 3 elementary particles called quarks. This was actually sort of discovered by a very famous scientist. His name is Gell-Mann, and with his collaborators Weig. He found out using group theory in mathematics, and experimental results that were available at that time showed that proton is not just point-like particle. It is made up of these elementary particles called quarks. Okay, there are 2 types of quarks called up type quarks, and there is another quark called down type quarks. All these quarks constitute the proton. Okay, now if you know the proton is made up of these 3 quarks, then if you know the masses of these quarks, okay, it is simple mathematics to find out the mass of the proton in terms of the masses of the quarks, and masses of the quarks are given inside this box. Okay, it's about 2.2 MeV over c square. They are all of the same order, and if you add all the masses, what you get is actually 9.1 million electron volt over c square. Okay, the mass of a proton that you measure, that we all know, is not actually 9.1, it is 938. So the surprise that we get by just believing this model and taking forward and calculating the mass of the proton is that you get about 100 times larger mass that we see in nature, but however the experimental or theoretical prediction is about 9.1. So one solution to this problem is actually to sort of discard this idea, but of course you cannot just like that discard because of one particular case. One finds that actually there are many results in physics that favors this picture that Gell-Mann and Zweig gave. So we need to understand why there is a discrepancy, that simple arithmetic sum of the masses of the elementary particles quarks is not giving the mass, the real mass of the proton, which is 938, okay, which is really 100 times smaller actually, what we get from theory. Okay, how do I understand this actually? If I want to understand this, what is this mass? Okay, do we have understood mass instead of finding the how much it constitutes and things like that, just the question that what is this mass? Okay, and this how am I going to solve this puzzle actually, that this arithmetic sum is not giving me the mass that we see or measure for the proton and neutron. Okay, so this table that we get, if it is reality, then it should explain the masses of all the hadrons, like protons, neutrons, lambda particle, and all that masses we should be able to explain using this picture. So it's a big question that we need to answer. Okay, so I want to sort of bring you something that you have learnt in your elementary schools. Okay, for example, you might have seen things like Newton's law of motion and then Newton's law of gravity actually. Okay, and these two laws contain a parameter called mass actually. Okay, so one mass that appears in Newton's law tells you about the the tendency to or resistance to the force that is applied on the body actually. The body actually it sort of resist to sort of adjust to this force that applied, and this resistance it's not resistant in the terms of physics terms actually. It is just inertia that a body sort of react exerts to this external force we call actually the mass. Okay, that's called inertial mass actually. There's also another mass which is called the gravitational mass. That is, if you apple falling from a tree, okay, experiences a gravitational force, and that gravitational force is actually proportional to the acceleration to the gravity, and this proportionality constant we call gravitational mass actually. Now people, these famous people had this question whether these two masses, one is coming because there is an attraction from the earth, another one is actually is a tendency to sort of oppose the force that is applied on it actually. So these are two parameters that appear in two different contexts, completely different from each other. One is nothing to do with gravity, another is something to do with the gravity. Okay, so this inertial and gravitational mass a priori it's not clear whether they are same. Okay, this question remained very, very long, centuries actually. Okay, whether these two masses are same. Experimental observation told us that they were very, very close to each other. Okay, it was Einstein who actually, while he was sitting in a cafeteria having coffee, and that time he was actually a clerk in a patent office, he asked this question, are these masses same? Okay, and he found out actually they should not be different, they are same. And then he found out this answer by sort of devising a thought experiment. The thought experiment is the following, that if a person sitting in a room and seeing an object falling in front of him, he can interpret that as the motion due to the gravitation acceleration is due to the gravitational force. And suppose the same man actually if he is sitting in a kind of a box which is closed in the next figure, okay, far away from earth where there is no gravitational field, okay, but the box that where he is sitting in is accelerating with the constant acceleration with the is about 9.8, then if he just sort of leaves an apple or an object from his hand, that object would look as if it is falling on the floor of the the box, okay, which means the two events or two experiments that one experiences, sees, okay, one on the earth and one on the accelerating lift or whatever or a spaceship, okay, these two things would look exactly identical. In one case it's the motion of the object is due to acceleration to gravity. In other case the same result will one observes if the experiment is done in an accelerating system. Which so he brought out some equivalence principle which is called Einstein's equivalence principle, and that tells you that they are not actually different, they are one and the same. Okay, that led to what is called general theory of relativity, and this general theory of relativity, as you all know, plays a very important role in our day-to-day life. Okay, if you don't know general theory of relativity, if you have not understood, if Einstein had not given this general theory of relativity, we would not have been able to actually fly in aeroplane, because we cannot keep track of the timings actually. Okay, t GPS that we all know. Okay, GPS works based on what Einstein actually proposed, the general theory of relativity. I will explain to you at some point how GPS works and how the Einstein work on finding the position of an object. Okay, it's like a car or a any object using GPS will be about 11 kilometers in a day. That means every day you will make an error of specifying a position of an object on earth by 11 kilometers. That means everything will go completely wrong if you don't take into account the work of Albert Einstein on general theory of relativity. So that's an important result. This result came simply because he asked this question whether these two masses are same or different, and by finding an answer to this very important question, that he could actually give a theory of for gravitational physics, and that as an application in day-to-day life like GPS. So GPS works simply because Einstein had given a correction to this 11 kilometers per day very correctly, and that helps actually to find the location of a car or a plane or many things actually in our life. Even mobile phone cannot work without correct GPS actually. So anyway, so not only he did that, he also actually studied how mass can be related to energy. That is a very famous relation called energy and mass relation, E is equal to mc square, that we are all familiar, and is also actually found that this mass that we see in nature is not constant. It depends on the frame of reference actually. Okay, if you take a rest mass of m0 in the rest frame, and if you see this mass from moving frame, it will be different. Okay, and he said that if give me a mass, I can convert into energy, and if you give energy, I can convert this into mass. So this formula is a very, very important relation, which tells you how one can convert energy into mass and mass into energy actually. Okay, and without this we cannot actually have explain nuclear fusion actually. Nuclear fusion, we all know, is the mechanism that fuels enormous amount of energy in the sun, and if you don't have a fusion, okay, if there is no conversion of mass into energy, okay, sun will not actually shine. Okay, sun shines for various reasons, and this is one of the reasons. Sun shines also because of quantum mechanics that I will not discuss today, but you can understand the importance of understanding this mass and energy relation. Okay, thanks to Einstein, that we now understand how sun actually burns, okay, and gives lots and lots of energy, and because of that we survive actually. And this slide basically tells you if deuterium and tritium fuses, it will give you a product whose mass will be slightly less than the sum of masses of this deuterium and tritium, and the difference in the mass is actually converted into energy. That actually is what we see as large amount of heat coming from the sun. Okay, another relation that Einstein wanted to sort of explore is actually if you give energy using the same relation, you can actually get the mass actually. For example, if you give me large amount of energy in the form of work or whatever, I will be able to convert this into mass. Okay, you can create new elements, you can produce large amount of protons and neutrons and electrons in colliding beams with very high energy. That energies are converted into particles. So this is a another application of Einstein's energy momentum relation, energy mass relation, E is equal to mc square. Okay, this is a slide which tells you how one can actually create particles having certain mass if you pump in lots and lots of energy. It's just a reverse mechanism of sun. For example, you can if you know the large amount of energy, then you can convert. Now this is, how is this related to that one that I was talking about, the difference between the sum of the masses of the quarks and the real mass of the proton. Okay, now this provides a beautiful resolution to this puzzle that I mentioned. Now if you assume that these elementary particles that constitute the proton are not just hanging around without talking to each other, but they hang around and also interact with them. Okay, interaction means there is a energy, they kick each other, okay, they jump on each other, and this kind of an interactions between them, you can think of this as an energy, lump of energies. Actually this lump of energies, Einstein actually already told us, can be thought of as mass. Okay, so that's an explanation for relating mass with the energy, and then you can actually think of a theory which can actually really explain that the energies among these point like objects inside the proton can be thought of as the mass, and that mass can actually explain the missing mass that I mentioned, that there is a deficiency. There is a 1:900, about this 900 or 100 times, sorry, 1:90 or 100 times this mass is because of there is a huge amount of energy that we are not adding actually. If you correctly add, okay, using theories that I am not going to explain to you, but there are a lot of development that took place to really quantify this, that simple terms that I sort of elaborated. Okay, you can actually put it in nice mathematics, okay, in the name called gauge theories, and try to sort of explain that using a theory called quantum chromodynamics. Okay, and this theory was actually developed by these three gentlemen who showed that the particles inside the proton are not actually living without interacting with each other, but actually they interact actually. So now the picture of the proton is not just the three particles it is hanging around. There are many particles, okay, which are hanging around inside, and these particles are because of some interactions between these quarks that I mentioned. Okay, so you can think of these energies as particles or particles as energy thanks to Einstein, and you can actually explain why the proton mass is 900 about 1 GeV, or whatever the number that I quoted in one of the slides, that it is so tiny by just assuming that the quarks inside the proton are not quite, they interact very violently among each other and because of this violent interaction they contain large amount of energy, and that large amount of energy can be thought of as the mass deficiency that we see. So this is the kind of a budget of the proton. Proton contains 9% of condensate, 32% of energy coming from quarks, 37% of energy from gluon, and then anomalous gluon. If you add all of them, you can explain the mass of the proton. Okay, so this is the understanding that we have now. We have complete understanding of proton. Okay, now if you understand the proton mass in terms of the quark mass and the energies, we are through. Okay, and I also wanted to give you some simple physics picture why these quarks inside the protons can give you so much of energy. Okay, the reason is actually quantum mechanics. I did not touch upon this quantum mechanics. Now you will see why quantum mechanics is so important in our understanding of protons mass. Okay, the quantum mechanics tells basically that there is some uncertainty relation, which basically translates to this simple, picture, that if you can measure, distances very, very precisely, you will not be able to measure the momentum of that object that precisely. So there you will have a kind of a compromise on the momentum. Okay, this basically translates that if you put, particles at a, in a very, very small distance scales. For example, you put all the quarks in a distance scale of 10 power minus 15 meters, then they are all, packed very, very, in a very, very small, region, and uncertainty principle tells if you pack them at very small distances, their energies will be very, very large, momentum will be very large, which basically tells you that objects which are confined in a very small region can have a very, very large amount of energy, and that large amount of energy, thanks to Einstein, can be thought of as the mass. Okay, that mass difference is what actually gives you this picture actually. So we know if elementary particles have masses and they interact, then you can explain the mass of the proton and neutron, and if you know mass of the proton and neutron and the number of masses of the proton and neutrons in the universe, you can add all of them and explain the mass of the universe, that 5% of the universe that we see. Now I want to ask in the remaining time the following question, that how you are going to explain that the quarks and these particles that we see, elementary particles, how they acquire masses actually. Okay, this is another question that we would like to ask, because maybe there will be surprises, there will be some interesting discoveries, and these discoveries can lead to, interesting applications like GPS. Okay, so that's why you have to be extremely curious to ask questions, and these questions one day can lead to revolutions in, technological developments, and that will uplift our way in which we live. Okay, so this question was asked about, 100 years before, and people worked very hard to find out how quarks acquire masses. I said quarks have masses, tiny masses. Okay, quarks are not made up of, elementary particles, they are point-like particles. How do they get mass actually? Okay, so the explanation for, the origin of mass, okay, comes from a mechanism called Higgs mechanism. Okay, and this Higgs mechanism basically tells you the following. Okay, I will not go into the details, but I will put it in a very simple terms, which is the following. So if you assume the elementary particles that we see, quarks, leptons, okay, if they live in a completely, free space called vacuum, okay, there is no other particles, there is nothing, okay, empty space, okay, then these particles will be in principle, the mass will be extremely tiny, but we cannot know. But if I want to explain why there is a mass, okay, I will have to actually relax this picture to the picture that these particles are not actually living in a completely, space of nothing, but it lives in a space filled
energy
by, sorry, can I continue?
Please
Yes, sir.
continue.
Yeah, so the particles, they don't live in a, very free space, but it lives in a space which is filled, by a field called Higgs field. Okay, this is just the name of a person. Okay, you can imagine that you enter into a room where the room is filled with the light, electromagnetic waves, something like that actually. So if you imagine the particles, elementary particles that constitute our, all our particles that we see are not living in vacuum, but live in a space filled with a field called Higgs field. It's like a fluid, you can imagine, okay, in the space time. Then the interaction of these elementary particles with the fluid, okay, can result, as I said, interaction gives you energy, that energy you can think of it as a mass. Okay. So, if these elementary particles interact with this fluid, that interaction you can convert into the mass of the particles. So, it is like I am sort of massless person. Okay. If I do not have any interaction among the things around, and if I start interacting with surroundings, then I acquire masses actually. So, this is a very simple minded picture. Okay. So, it is like this actually, the particle acquire masses because of the surroundings actually. This picture was actually developed by 3 people. Okay. One of them is Higgs, and hence this mechanism was named after Higgs. Okay. This slide is a very famous slide when the Higgs particle, this Higgs mechanism was actually sort of confirmed by experiments. Okay. This basically tells you the following actually. This picture basically tells you if you start from 1 to 5, okay, imagine there is a room where a lot of scientists are sitting, okay, and all they know is actually that Einstein is going to visit this hall and give a lecture. Okay. So, before Einstein comes, the room is very quiet, they do not interact with each other. Okay. So, you can think of this as like a our space, that space filled with Higgs field. Okay. It is very quiet. Now, Einstein enters. Once he starts entering, everybody starts looking at him in the direction of Einstein, that is the the cartoons number 2, and then there is some kind of a disturbance. Each one tells, oh, this is Einstein who is entering this room, and some of you have to talk to him, influence him, get all the answers that we have in our mind, and this is something going on actually. In the slide 3, once he enters and goes center, you can see people clustering around him actually. Okay. And then Einstein is not completely alone, but he is actually surrounded by too many people. As you can see, this this surrounded people are put in yellow color actually in this third one actually. So, Einstein is sort of shielded by this people. Okay. So, if you think of Einstein as a particle and the people around them are a Higgs field, so as soon as Einstein enters, there is a field of people actually around him clustering actually. Okay. And this picture continues, okay, that if he starts moving in the crowd, you can see his motion will be kind of restricted actually, because there are people asking questions because of interactions with motion. So, now this very simple and elegant picture of the motion of Einstein in the crowd basically translates to a particle in the presence of Higgs field. Okay. Einstein, without this people, can actually move around in the room very freely as if he is massless particle. Massless particles can move around. If a person is very heavy, you won't be able to move around. Okay. So, it is like very light person, he can move around. The same person in the presence of people, he will be actually distracted by many things, and his motion will be, but of course his mass is not changed, but it is more like if you just only look at his motion, not the people around, it would look as if Einstein has gained a lot of mass, that is why he was unable to move around. So, this simple picture, that interaction of the particle with the surroundings, okay, brings some kind of energy, and that energy you can think of it as a mass, and that is the mass that Einstein or particle sort of acquired, and that made that person to move slowly or the person to behave differently. So, this simple minded picture basically tells you, this mixed mechanism tells you that elementary particles in the presence of this fluid, Higgs fluid, okay, they acquire masses because they interact with that fluid and gain energy, and the energy is converted into mass thanks to Einstein, who said actually energy and mass are related through E is equal to mc square, and that is how all the elementary particles acquire mass. Now, we start getting better and better picture of how the 5% of the universe has a specific mass. So the answer to this question is actually that this 5% of the universe get masses from molecules. I mean, you can even answer it. It gets masses from all the galaxies. Galaxies get masses from various stars in it and planets in it, debris in it, and each debris you can think of it as a molecules, and molecules masses, if you add, you will get the mass of the this debris, and the molecules get masses from proton and electron, and proton gets masses from quarks, and the quarks get now masses from the interaction of the quarks with the Higgs fluid actually. So this is the kind of picture that we start getting if you ask the big question like how universe get masses. Okay, so you in the process from very large scales we managed to actually come to very small scales like 10 power minus 15 meter distances. Okay, unimaginably small space, and understand the physics that is happening there. And in the journey not only we unraveled the the nature, understood origin of many things, we could also exploit all these things in day to day life like GPS and semiconductors. Semiconductor for example is a result of quantum mechanics, and so without semiconductors we cannot have any electronic equipments like my laptop or a mobile or anything, and without Einstein theory the entire traffic in our world will freeze actually. If you remove GPS for half a minute, and there will be accidents everywhere actually, because GPS measures the distances so precisely, and that is the success of these understanding. The understanding comes because we have interesting questions. It may sound very simple, the question, but the simple questions leads to very profound answers.
Absolutely.
Profound
Ravi,
explanations.
Ravi,
Right.
probably we are getting lot. I mean, we are taking too much,
yeah.
overcarrying it.
Yeah.
Probably you can wind up within a minute or so,
Yeah,
so that
Yeah, I'm
and we will
finishing
have
actually.
another session too.
Yeah.
yeah, I
please.
am finishing in 2 minutes actually.
Please.
And
please
now,
go ahead.
yeah, so this understanding of the origin of mass led to many interesting developments in science. Many developments in science led to many developments in technology, and of course all these theories need to be tested and their predictions to be validated. And the last one that I discussed about the Higgs field and Higgs field that gives mass to all the elementary particles actually also tells you that there exists a particle called a Higgs particle, and the scientists spend good amount of time and energy to build experiments which are very sophisticated experiments. One of the experiment is in at Fermilab, USA. It's called Tevatron. Another experiment was built about 15 years before. It's called Large Hadron Collider, which collides particles to find out, like using Einstein principle, that Higgs particle exists in nature, because only if that exists then we can tell actually that that mechanism is the correct mechanism to explain the masses of the elementary particles. And this experiment is one of the biggest experiment on earth. Okay, about 10,000 scientists from all over the world participated, including India. Many scientists who contributed to these experiments to discover the Higgs particles. And it is it's about 27 kilometers circumference accelerator, and it is about 175 meters below the earth. There is a circular ring where the particles are accelerated and collided, The energy of the collider is about 70 eV each, and there are about 6 detectors people to place it so that you can catch that particle that we are looking for. And the experiment looks something like this actually. It's quite complicated. Okay, it's about 45 meters long, 7,000 tons. It's heavy, and all that. Okay, these are all just to show you that how complicated these experiments are to confirm that our understanding. Okay, and finally this experiment at CERN in Geneva managed to discover this particle. Okay, and the discovery led to our better understanding of the origin of mass in terms of what is called Higgs mechanism, and also through interactions. Okay, and because of this discovery, the theorist got Nobel Prize, and also experimentalists got Nobel Prize actually. So two Nobel Prize came in recent times for understanding the origin of mass. Okay, the origin of the mass that constitute our visible universe, this 5% of the universe, and we still are left with the question that is an unanswered question, which is, where does our universe get mass from? I said only 5% of the universe we have understood so far, and the 95% of the universe is called the dark part of the universe. It's called dark matter and dark energy, and we still have this question unanswered, and there are many experiments that are going on, and
Yes.
solving this problem can give you new physics, new developments. Thank you.
Thank you. Yes, yes, my dear friend Dr. Ravi. Yes, Ravindran, we have, fortunately you have find out some unknowns, but there are many unknowns which really unknown. So we have some unknowns, we have more than that unknown unknowns. So thank you very much, Dr. Ravindran, for describing such a complex situation, such a complex problem in such a simple term that even a layman, a lay student of science can understand it. But however, many things are still remaining to discuss on this topic. We will be calling you again. We would like to have you in our studio sometime, maybe in April or in May, so that we can have these discussions more elaborative, and we can take more questions along. Thank you very much, Dr. Ravindran, and thank you very much, Homi Bhabha National Institute. Thank you very much, Department of Atomic Energy, for collaborating with NCERT, New Delhi, for this purpose. It's all.
Thank you so much, Dr. Ravindran. Thank you so much, Dr. Gagan, for your wonderful contribution to the session. It was indeed, as Sir mentioned, that it is very understandable for a person like me who doesn't belong to the science background. So thank you once again to both the experts. Now it's time for me to wind up this session. Today we conducted the 97th edition of our webinar series titled Listening to Learn, and we talked about origin of mass. So here I'm closing this session, but before I leave, here is an important update for all of you out there. It is regarding Pariksha Par Charcha. So dear viewers, we hope you enjoyed Pariksha Pe Charcha 2025 with Honorable Prime Minister Shri Narendra Modi, and we are excited to announce that this year's edition brings a fresh perspective with 7 upcoming episodes featuring distinguished personalities across various fields. These sessions will cover essential topics including mental health, technology and finance, nutrition and mindfulness, aimed at guiding students in their journey of learning and personal growth. Let's watch some videos related to the same as well.
परीक्षा पे चर्चा के 8th एडिशन के नए अंदाज में हो चुकी है शुरुआत। प्रधानमंत्री नरेंद्र मोदी जी ने स्टूडेंट्स को दिए एग्जाम और लाइफ से जुड़े वैल्यूएबल टिप्स। आगे इस चर्चा से जुड़ेंगे अलग अलग फील्ड्स के एक्सपर्ट्स जैसे दीपिका पादुकोण, मैरी कॉम, फूड फार्मर, सदगुरु इत्यादि, जो 7 नए एपिसोड्स में एडवाइस देंगे मेंटल हेल्थ, न्यूट्रिशन एंड वेलबींग के बारे में। तो देखना ना भूलें 12 फरवरी से रोज सुबह 10 बजे डीडी न्यूज और नरेंद्र मोदी यूट्यूब चैनल पर।
So that was quite an interesting video, and please tune in from 12th to 15th of February 2025 at 10 a.m. live on Doordarshan channels, and don't miss out on these invaluable insights during this occasion of Pariksha Pe Charcha. Thank you so much. With this is a wrap. This is me, Harpreet Kaur, taking leave of you. Namaskar.